Okay, wonderful. It's now 12:01. This is Michael McClellan with L3 Levine Electronics and Electrics. What you've come to is a Lunch and Learn webcast with Jorgen Madsen. And Jorgen, we are very lucky to have Jorgen. Jorgen is stuck at his home like a lot of us in upstate New York. So he has time, I guess, for these webcasts. So we're very lucky to have him. A couple of housekeeping items. This is a webcast, so your phone is muted. We would love for you to participate. There's a question button on the right side of your screen where you can press that button and ask questions of and Jorgen. There's also some handouts that we've attached to the presentation so that you can download those during the presentation, maybe examine them, and you might think of a question during the presentation. So without further ado, I'm going to turn it over to Jorgen.
Well, thank you very much, Michael. And yes, I am stuck at home like everybody else. Things could be worse, right? And regardless, I'll be more than happy to present or answer questions of whatever may be required at any time. So thank you for that. My name is Jorgen Madsen. I'm with ABB, ABB's power protection business, which is part of the electrification business under Smart Power. And what we do is a mission critical equipment. So it's practically everything from parallel and gear, ATS, UPS, and then power distribution, STS, PDUs. Today I will be talking about UPS, and I will take a little bit of a trip down memory lane as an introduction as to what is it, where did it come from, how has it developed, and why. And there are some technology drivers and some market drivers that has driven the UPSs to look like what they look like today, and two, driven the people to configure UPSs the way they configure them today. So I'll talk about that, including some of the pros and cons with the different options, the different configurations, and then finish off with just a running through the current offering on the UPS side and the features with the ABB's current UPS offering. And I finally just finish off by dialing into a very important part of the UPS. It doesn't work without energy storage, and there's a lot of things going on in that field as well. So I'll try to touch as much as on everything. And then, like as Michael said, please feel free to ask questions. I'll be more than happy to do. Well, I will do my best to try and answer at the end of this. So jumping into the presentation, like I said, like the start is what and why, and the reason for this slide is, if nothing else, I think 98% of UPS presentations out there have a very similar slide, or at least this is what the sales engineer would present to the customer. There's a critical load, it needs AC power, it gets that from the utility, but as we all know, it's not always clean, it's not always stable or uninterrupted. That's where the UPS comes in. It just takes whatever it gets from the utility and makes sure that there's always a uninterrupted clean power for a critical load. And the drawing at the bottom of this slide shows a single line of a typical UPS. And there are, like, historically over the last several decades, there have been a number of different configurations and UPS designs, but this is how it started. This is pretty much where we are with, like, probably more than 99% of the UPSs. And just basic what's inside the box. There are 3 power modules if you look at the drawing, power would come from a utility on the left side. It'll get to a rectifier module that does what the name states. It rectifies that AC power to DC, and then it's feeding that via a bus to the inverter. And the inverter does what that name says. It inverts that DC power back to AC and creates the clean regulated 480 volt alternative to 208 in the US for the critical load. So some might argue that sounds like a little bit like back and forth. We go from AC to DC and then back again. The reason for that is that for the UPS to be uninterrupted, we need energy storage. And so far, we've only figured out how to do that at AC. So between the two power models, there's a battery energy storage device. Today, almost entirely batteries of one form or the other. That is a DC energy storage. So the inverter will have DC power, whether there's coming DC power from the utility via the rectifier or not. If utility power fails, the inverter will just take DC power from the battery and continue to support uninterrupted power as long as there's energy on the battery, or until the rectifier kicks in again. So that's the basic functionality. That's what makes the UPS and what makes it uninterrupted. There's one last power model in all major UPSs today that's referred to as a static switch, or static bypass switch. And it's, in lack of a better word, it's a save the day device. The static switch, it's part of the UPS. And the UPS is constantly monitoring its own output, the stable 480 volts for the critical load. And if something happens, so the inverter cannot maintain that. Like the inverter is a limited power source. If it's 100 kVA, it's 100 kVA inverter. If there's an overload or a short circuit or similar to that downstream that exceeds what the inverter can handle, the voltage will drop. But the UPS control will see that, and it'll immediately transfer the load directly to utility power by firing the static switch. This happens in less than a quarter cycle, and which is what still would be considered uninterrupted, not critical for the load at all. So those are the main functions of the components. Then, in case of the overload or short circuit, when the overload had been cleared by tripping a breaker, typically downstream, the UPS will automatically go back in the inverter supply. So one more comment about the static switch, and there's a buzzword in the industry is referred to as economy mode. But because like any other electrical or electronic equipment, when you convert power, you create heat. There's heat loss. So in the online mode, going from like utility rectifier to the inverter and out, both the rectifier and the inverter have heat loss. It's not nearly as much today as it was a few decades ago. In modern UPSs are very highly efficient, but there's still, even in big UPSs, around 3% heat loss. And UPS manufacturers figured out a couple of decades ago that if you fire the static switch and use that as the normal mode, then power is coming directly from the utility going to the load, and now we only have the losses in the static switch, which is roughly at 1%. So now the efficiency is suddenly 99% for this system. So it's been around for a long time. Hardly anybody uses it because that's not why they bought a UPS in the first place. Because now the power is being fed directly from the utility. Whatever noise may come in may be able to make it to the static switch to the critical load and cause problems. The inverter will, in economy mode, the inverter will be able to kick in automatically and start to feed power in less than a quarter cycle. So that part of the operation is not critical. It's more the notion or that little nagging doubt in the back of the facility manager that something has to happen. If power fails when they are in economy mode, the inverter has to kick in. And the fact that there's unfiltered power. So economy mode it's in a lot of UPS specs today. Hardly any, like all UPSs can do it. Practically all UPSs can do it. All ABB UPSs can, but hardly any customers ever use it. So that was a lot about the first slide, but I'd like an introduction to what this is. So I got two slides just illustrating where does this UPS fit in. And typically you got utility power, a little bit more details. This is what a typical data center could look like with utility power or generator power as backup power into the data center, then the UPS sitting there cleaning everything up before the power is fed into the IT load, to the critical load. This is just a slightly different way of seeing it, but again, showing the UPS as the guard between power from utility at the generator and then what is fed down the power lines, down the distribution equipment, down to the critical load. So looking into how did this all start and what has happened? Static UPSs have actually been around since the 60s. And actually started when somebody invented a silicon conductive rectifier, an SCR, and smart engineers figured out that there were a number of different ways that they could utilize that component. One of them was as a UPS. So the first UPSs are actually from the 60s and based on SCRs. Functionality is the same as we just talked about. The single line, that's what it looked like back then, still today. The drawback with the SCRs is that we can gate them on, but we need a zero crossing off, we need to do fair force commutation to switch them off. So it's a very solid, rugged device. But the harmonics was a big thing, a big issue with early generation UPSs. First of all, the rectifier would generate a lot of harmonics that would be fed back up the power lines. And on the inverter would, in some cases, just be a 60 hertz square wave. In best case, like this, could be a step wave, but would require significant filtering to look like a sine wave, which was required for the critical load. So that's where we started out with static UPSs. Over the years, we have gone from like better semiconductors becoming available, like from the SCR to bipolar transistors and now to IGBTs. And a transistor as well, an IGBT is a transistor, is a device that we can actually switch on and off very fast as needed. And UPSs today are based on what we call PWM, pulse width modulating control, where instead of just with the SCR having a step wave or a square wave, we're still switching between a positive and a zero crossing, or positive and a negative on the DC side. But with very fast switching, there's a pulse train where the pulse width is regulated so that it's as close to an ideal sine wave as possible. We've seen two-level inverters with primarily with the bipolar transistors, and then lately most UPSs are based on three-level PWM, and it's all about getting a waveform that's as close to an ideal sine wave as possible. It's still tiny little square waves, but very close to an ideal sine wave. So UPSs still need filters to filter the harmonics out and make it a sine wave, but very, very small compared to 50 years ago, or even 20 years ago. So a little technology. So in line with the same, and actually this is the picture, which is not great quality, but interesting historically. That's actually a GE UPS from the late 60s, 185 kVA, based with a design that's exactly as I just described, based on SCRs, SCR rectifier, SCR inverters. And the single line, the two at the bottom, the one on the left is like what the UPSs would have looked like, or did look like back in the 60s, 70s, 80s actually, and even a little later than that, with transformers and what could have been shown, but not as detailed here. Very big filters, big inductors, big capacitor filters to filter out the harmonics. There were two reasons for all the filtering and the transformers. One was to filter out the harmonics, as I mentioned. The other was that the first generations of semiconductors, the SGRs and the first transistors, had a fairly low voltage rating. So they could not operate at full line voltage. So the UPS design, the transformer actually stepped on the input, would step the voltage down to something the SGRs or the transistors could safely operate and similar in the inverter, on the output of the inverter, there would be a lower AC output from the inverter, but the transformer would step that up to 480. That was the reason, and that was just out of necessity. The filters were needed, the transformers were needed. Since then, with the modern IGBTs that are like easily way more than normal, available to handle way more than normal line voltage and very fast switching, we don't need the transformers. We don't need the filters, at least with very limited filters. The benefit, of course, is we got rid of all that heavy magnetics, and with that, a lot of the heat loss in UPSs. So that's kind of compared to then, very high efficiency, very compact, very light compared to yesteryear's UPS design. But they work pretty much the same way. So this slide just illustrates it's just a step in the business, and I've been in this business for a long time, not this long, but the efficiency have been one of the driving factors and a big focus areas for customers for many years. Not so much today. Today, UPSs are just expected to be high efficient. But with the different development from SGRs to transistors in the beginning, all based on needed transformers and a lot of magnetics, into IGBTs, and then the first transformerless UPSs up to where we are today with what I would call a second generation transformerless UPS, IGBT based, typically with 3-level PWM for the rectifier and the inverter. Most UPSs, efficiency wise, are very close to 97, between 96 and 97, but typically very close to 97%. So very low heat loss compared to the heat loss of the first UPS, even a couple of decades ago. Like the economy mode I mentioned, and I have that little green dot and on top of the steps here, where we will get up to 99%. There would have been a huge saving if people had picked economy mode when it first started becoming available a couple of decades ago. People didn't do it then, and today there's even less of an incentive to do it, because you save a little bit on the efficiency or on the losses, but really not an awful lot. And then I should add, there actually probably is one more step here, because we are seeing like a new generation of semiconductors, silicon carbide, are becoming available. One UPS manufacturers have started using them, but only in one UPS, and they actually did not use it in the latest generation. Silicon carbide have even less losses compared to IGBTs, and with that we can get the efficiency of very close, around 98% in double conversion online mode, which of course will lower the incentive for economy mode even more. So I believe the silicon carbide will be the future, but still it's more expensive. The components are more expensive, and to the point that it does not justify the 1% percentage gain as of yet. Similar with a lot of other things, as you have bigger volume in manufacturing and improve your development in manufacturing process, costs will come down. We're not there yet. So today, with the majority of UPS's efficiency is just shy of 97%. So now, like the single line that I showed before with the UPS, that, like I said, this is probably 99% of the UPSs out there. UPS manufacturers have come up with a number of different designs based on, including based on this design. And what we have today, we have a mix of what is referred to as a monolithic UPS, which is a traditional. that 185 kVA GE UPS, that was a monolithic UPS. What that essentially means is that the UPS is what it is. Historically, a 500 kVA UPS would have a 500 kVA rectifier, 500 kVA inverter, and the static switch would support 500 kVA. That's what it is. That's all it knows, and that's what it can do. If customers need more power, they will just parallel another 500 kVA to that one, or more of them, for just to support additional power, or one extra one if they would like some redundancy. So the picture on the right, UPS manufacturers came up with what is today known as modular scalable UPSs, which is essentially installing smaller power modules in a bigger UPS frame. And the one shown here is an ABB 500 kW UPS, and the single line shows what it looks like with the doors open of the electrically. It's 5 small UPSs in parallel. So the benefit with this is that there's a much bigger or greater scalability compared to a monolithic UPS. The customer can buy the frame, the 500 kW frame, and then they can, depending on what they need today, they can put 1 or 2 or 3 power modules in there and then add more as they need them, like postpone the capital expenses. But in both cases, both the monolithic and the parallel or the modular can be paralleled to get to bigger power than 500 kW. And these are just examples. There are a number of different designs out there with different manufacturers of both monolithic and modular UPSs. And regardless, and I mentioned this already, all the UPSs can be paralleled. So this big black train and in the top right corner here actually shows 6 modular UPSs in parallel. So 6 times 500 would support 3 MVA of power. It's possible. It doesn't happen often, but it's possible. But all of the UPSs, regardless of size, can be paralleled. Like the drawing in the lower left corner shows 3 UPSs. If that 3, say, stick to the 500 kVA. If it's 3 500 kW, that configuration would support 1500 kW. But it could also be seen as a 1 megawatt with an N+1 redundancy. So most manufacturers can parallel UPSs. All ABB UPSs are parallelable. Typically, depending on manufacturer, you can parallel 6 or 8 units. You hardly ever see that many, but technically it's possible. So much about the technical side and what's behind the skin of the UPS, and then looking a little bit into what I would call like market driven, or what has driven the how people configure UPSs, and that has primarily been driven by the market and what the market needed. And we have, especially over the last decade, actually a little bit more than that, but we've seen the market develop from a model where every corporation, every enterprise, every company had their own data center. Whether that was just a couple of servers in a closet somewhere, or for a bigger company would be a large data center. That was a model until somebody came up with, well, we could actually build your data center for you. Like, we'll build the building and put the power and the cooling in there, and you can just rent space, like the colo model. And we've seen that gain a lot of popularity. And then very shortly after that, also what we know as the cloud module. Now companies are building like complete data centers with everything. And you just, instead of renting and paying for space and power and cooling, now you pay for computing power and storage. So we see less and less of the. They're still around, and they will. Like if you look at the market today, there are still the corporate type or enterprise type data centers. Financial institutions typically have their own data centers. We see this with in the healthcare sector also. They're typically not that big, but by law, there are patient privacy laws that they have to adhere to, and for that reason often have their own data centers. In many cases, non-critical part of the operation, whether it could a financial institution or a hospital, they may utilize colo or cloud for part of their computing needs, but they typically have their own data center also. And then the majority of the build out, the majority of we see is hyperscale, like very large data centers built by colos or cloud providers. And then in the middle, and I haven't talked a lot about that, but it's certainly very much talked about, is edge computing, which typically is a containerized solution placed close to where the data is being generated and needed. The market is still, for a few years, have been talking a lot about it and still trying to figure out how to handle this. But what it boils down to is that there's just an unlimited, seems like an unlimited amount of appetite for data, and it's just getting worse. Well, if that's probably not the right term, but I can imagine with self-driving cars and the amounts of data that'll have to be handled, and then suddenly, especially in the self-driving car, latency starts to become an issue. Like the speed of light is pretty quick, but that may not be fast enough. So we the majority of what we are seeing right now is on the cloud, colo and cloud side. It's coming, and we're clearly going to see more and more of that. Some of the data processing has to happen locally, just in the interest of speed. So looking at a couple of configurations, and then obviously customers like the first drawing I showed, it can be just one load with one UPS, or the customer can add another UPS for extra capacity, or maybe 3 UPSs for capacity and redundancy. So it all depends. There are hundreds, if not thousands, of different ways of configuring that, depending on the criticality and of course budget. The configuration I'm showing here is what was very commonly used in large data centers pretty much until the colo cloud area. There's some financial institutions that still would use something like this, but even they are not doing this. It's referred to as the system redundant, or 2N+1. The Uptime Institute, that's an organization that actually came up with a way of great data centers and came up with like a tier level certification where tier 1, 2, 3, 4, it's not used anymore, but a tier 4 data center would be a data center that was like known as fault tolerant and concurrent maintainable. And in the drawing here, there's like two, you can look at the center, the power down the line as an A bus, and the other one as a B side. Both are feeding the same load. So there's redundancy on UPSs on the A side and the B side. Practically anything can go wrong on both sides, and it's not going to affect the power to the load. There will be some way of getting power to the load from the B side or from a bypass. They will typically be more detailed or complicated than this single line. So it works great, and it's very highly available, very high availability. The drawback is that the utilization is low. Utilization has become a buzzword in the industry over the last several years, because for this to work, that you have to be able to lose the entire left side, and the other side has to be able to support the load, ideally still with redundancy on the UPS side. As a rule of thumb, the utilization of everything is less than 40%. So this means that if a customer needed to back up a megawatt, just to pick a nice of say 400 kVA, they would need to invest in a megawatt of hardware to support that. And that kind of worked in the corporate enterprise side, because the data center was part of the corporation and the cost kind of drowned in. And there was a period of time where the buzzword like uptime is king, regardless of the cost. That changed completely with the colo and cloud model, because now we have separate, different cloud providers competing with each other and cloud providers competing with each other. Now the data center is a revenue generator. So as I mentioned, efficiency, that's still very important, but they are very focused on coming up with designs now where they can actually increase the utilization, still have a highly reliable system, but not with a lot of like the just idling equipment sitting around as we see in the system redundant, like a 2N+1 system. So today we typically see two like main schools of thought or designs out there. One is what's referred to as a block redundant, also, or a catcher system, which is they come in all different ways and shapes and forms also. But this one just showing 4 UPSs, like 4 systems, each like 3 main UPSs and a catcher UPS. Each main UPS is feeding its own load. And the catcher UPS is just sitting idle, not really doing anything, except it's sitting there ready to take over. So if something happens to UPS number 1, the static transfer switch will just automatically transfer the load to the catcher UPS. The benefit with this is now we have 4 UPSs, but we can load 3 of them up to 100%. So now we increase the utilization up to 75%. So this just shows 4 UPSs. I've seen catcher systems with up to 8 or 9 UPSs with 1 catcher. And of course, you don't gain as much. Like if you had 5 UPSs instead of 4 in this one, now you would have 4 main UPSs and 1 catcher. That would bump the utilization up only from 75 to 80%. But of course, it still matters. So going to 6, 7, and 8, it still improves utilization, but it's diminishing percentage-wise. So this is one popular design of we see for large data centers now. Compared to the other one, this one is fairly easy to handle because the load is supported by each main UPS, and as load is added, the UPS will tell you if it's overloaded. The concern that some people have with this is that the catcher UPS is sitting idle. It's running, but it's not doing anything. And then if something happens, it has to take a full, typically 100% load step. But it's a very popular configuration. We see a lot of those. The other one we see is what's referred to as a distributed redundant system, which is similar in some ways, and same as the catcher system I showed. This is, I also show this one with 4 UPSs, and of course in both of them I show 1 UPS, but this could be 2 UPSs in parallel or 3. And each UPS here could be 2 or more UPSs in parallel. Actually, very popular right now for both configurations is a total UPS capacity about 2 megawatts, and that could be 2 1 megs in parallel or equivalent. So the distributed redundant is also known as a 4N/3 or 4 to make 3, or like the catcher, you can add systems. So I've seen 8 to make 7, at least on diagrams. And the way this works is that the load is divided between the UPSs. So UPS 1 is sharing its load with UPS 2, 3, and 4. So all UPSs are sharing the load, and it's balanced so that all UPSs are equally loaded. In this case, you can load them up to 75% of nominal capacity of the UPS. And if one UPS fails, the other 3 UPSs will now, if they can feed, like if UPS 3 fails, the load it's connected to will lose power from that side, but then they will get power from the backup, the other UPSs, 1, 2, and 4. They will now just go to 100% load. So it works. The tricky thing with this is that you can balance a load when you first build the data center, but it requires a good amount of effort to make sure that the redundancy is maintained in the system, because the UPS will not know. each UPS system will not know if it will be overloaded. If somebody sneaks in and installs some IT load in a place where it really shouldn't be, and it works as long as all UPSs work. But if one of them fails, one or more of the others may be overloaded. So it both the block and the distributed redundant systems offer very good, a much better utilization of the hardware, and we see both of them roughly equally in installations across the nation. But it takes a little bit on the distributor. It takes some effort to make sure that the redundancy is maintained. One last thing I'll mention on this, what we are seeing also is that some customers are moving to what they call a modular skid-based solution. And the skid is basically just a big steel frame. So instead of building a building and then installing your UPSs and your switchboard or switchgear and distribution in there, they built the building. And then, especially for colos, they install the UPSs they need with the space that's rented from day one. And then instead of having to install individual UPSs and switchgear and all that good stuff every time they have to expand and add more power, they install a skid, which will include a UPS, typically a UPS and the power distribution, and if required, also a static transfer switch. All pre-assembled at a factory, pre-assembled, pre-wired, and tested. So it's a fast way to add power. And it's not I almost said pluggable. Clearly, it doesn't plug into a wall outlet somewhere, but all you have to connect is the input and the output cable. So it's like a big UPS with everything you need to it in one package. We see that becoming certainly gaining popularity in some areas. And then going into, I said I was going to talk a little bit about APC's offering. ABB. Apologize for that. There are too many acronyms there. And on ABB, we make both monolithic and modular scalable type products. I'll just quickly go through the product offering. And we talked a little bit about so we've seen this single line before. That's a monolithic UPS. This is the 500 kW UPS shown with the doors open. That's what it is. That's what it knows. But it's the only way to add power is to parallel another 500 kW to this one. Could be a 1 megawatt also. So just quickly going through the ABB UPSs. There's the smallest member, and this is on the 480 volt, like talking data centers, so like small data centers and above, is what we call the mid-power TLE. It's available from 40 kW up to 150 kW. All of the UPSs, whether monolithic or modular, are IGBT-based rectifier and inverter. High efficiency, power factor corrected on the input, like a unity power factor rated. Can do economy mode, or e-boost is another name for economy mode. So the mid-power TLE from 40 to 150 kVA. The bigger brother, the high-power TLE, and that's that 500 which we saw before. It's available from 160 kVA up to 1 megawatt. But very, very similar IGBT-based modules, rectifier and inverter. So similar features, efficiency just shy of 97%. In online mode, they can do economy mode. So the high power TLE from 160 to 1 megawatt, and then the biggest member of the family on the monolithic side of also what's called a block UPS, a single block UPS, is a Megaflex, which is available from 1100 kW up to 1600 kW or 1.6 megawatt building blocks. All of them are parallelable, like to get to more power or redundancy. And as you look, just like the main features on the right of the slides here, they're very similar. They can do the same thing. It's just more power. One unique feature, and actually two things I'll point out with the MegaFlex is like one, it can handle high resistance grounding. We don't see that a lot in data centers. It's more often seen in the industrial applications, but once in a while we do come across it. So the smaller model cannot handle that, but the MegaFlex can do that. It's standard designed to operate and work in a high resistance grounding environment. The other thing, it's very compact. It's only 130 inches wide. 1.6 megawatt it's by far the most compact UPS in its size. For comparison, actually, the 1 megawatt TLE is 144 wide, and the 1 megawatt TLE is not a big UPS by any imagination. It's actually a fairly compact UPS. So footprint cost money too. So that was the main driver in the design is increase the power density of the UPS to save footprint. So I should mention, not going to talk an awful lot about that, but we have a line on smaller single phase UPSs and of course technically they are monolithic. They're not typically what we would consider in a data center environment. So the other side, or the other side, is the modular scalable type products, and I'll just quickly go through their couple. There's a 480 volt line of the modular scalable products. At 480 volt level, there are two different frame sizes. They're both based on the same power model, which we can actually see the left side of the cabinets. We have the power modules sitting there. That's a 100 kW power module. So 5 of them will fit in the 500 kW, and it'll support 500 kW. The smaller one will fit up to 3 and support up to 300 kW. Or of course with the 500 up, both of them. Actually, if the load is less than one less than what the power modules installed, the unit will offer redundancy for the critical load. So this just illustrating that little thing here is actually a 100 kW UPS. Same as the monolithic ones. It's an IGBT based rectifier and inverter. It's just a smaller one. And in the concept powered or DPA UPSs, we just fit more of them. So this is what the single line looks like. Actually, all of this is a 500 kW modular scalable UPS, fully populated. So in this one, there's 5 of the 100 kW modules. You close the door and it operates like a 500 kW. It'll support 500 kW any day, all day long. That's what it's designed to do. The benefit with the ABB modular UPSs is that the power modules are complete UPSs. So they operate like complete UPSs in parallel. There are no shared active components involved in controlling the operation. Every single of the little UPSs here can control the entire operation of the system. So as I mentioned before, if the load is support like one less of the power modules installed, like in this case up to 400 kW, this unit will offer a true N+1 redundancy in a single frame. And obviously, as more power is needed, it's possible to parallel this UPS as well to support higher loads. And quick, there's a smaller member of the modular types. There's a 208 volt. We have 2 different frames for this one as well. Very similar to the big brother, the 480 volts. Differences at it's 208 in and out, 208 120 in and out, and instead of a 100 kW module or UPS, it's a 20 kW UPS. 6 of them will fit in there, so it can support up to 120 kW, or what you could say 100 kW and with N+1 redundancy. That's very similar drawing. That's what it looks like. It's 6 small UPSs in parallel in one frame, but like the name of the modular scalable, customer can start with whatever they need today, and then they can add more as they need them. And finally, I call the DPA 120 the little brother. I guess this is then the baby brother. Is based on the same power model, so based on the 60 kW, but only space for three of them. So 3 times 20 kW makes up to 60, and then the remaining space is now utilized for built-in batteries. So if a customer doesn't need more than 60 kVA or 40 kW N+1, this is a solution. The other UPSs, all the other UPSs we talked about, need external battery cabinets for the energy storage. This one has space to have it built in. So for small data centers up to 60 kVA of data closets of 40 kW N+1, this saves space and it's clearly the optimum solution. And then just a few general comment on monitoring communication. Like all UPSs have a color touchscreen display on the front across the board, all of them. The reason for this, and this slide is from the modular system, is that the little one shown at the bottom here is to illustrate each power model in the modular products actually have their own display as well. So there's redundancy on the power models. If a power model should go bad, the remaining models can support the load no problem. But if the display on the front should go blank for whatever reason, you can operate the entire system from any of the little displays on every, whether it's a 208, the 20 kW, or the 480 volt, the 100 kW module. So there's redundancy on the operation as well. Monitoring wise, UPS is like the very first generations, and until maybe 20 years ago, a little bit more, this is what we did. There were relays, and there would be a flashing light or a big siren outside of the UPS room. All the UPSs have that still today. But what we see a lot more is like online monitoring. Modbus is in the data center market the most popular, but some use SNMP. The cooling guys, the mechanical guys, seem to like BACnet a lot. Profibus is primarily used in Europe, but it's a protocol that's mainly used in industrial applications. The short version of this is we support all of them with the ABB UPSs. And then quick, on the ancillary for all of the UPSs, there are matching or non-matching battery cabinets, input and output switchboard or switchgear, distribution of all battery solutions, but I'll get a little bit more into the battery solution. So the drawing here, or the picture here, basically just shows a 500 kW modular UPS with a 3-breaker bypass bolted to the side. It looks nice. Other than that, this could be part of the surrounding switchboard or switchgear as well. But like, it looks nice, and the energy storage, the battery could be in matching cabinet as well, making it one long lineup. And then to the energy storage side of things, and just quickly going over, and I guess this will be a little bit like down memory lane as well, because if we go back a couple of decades, by far the majority of large UPSs were installed with wet cell batteries. That has almost entirely changed to VRLA batteries today, because they're so much easier to deal with. Wet cell batteries have benefits. They live long. The failure mode, they usually fail shorted, which means if a cell fails, you don't lose a string, which you typically do in a VRLA battery. So some people really like wet cell batteries, but they require separate rooms. They require spill containment, eye wash stations, hydrogen monitoring, ventilation. And you need somebody to run around and top up the water. So the market has almost entirely moved away from this. There's still not 100%, but into something, a VRLA battery that's very easy to deal with, installed in a steel cabinet, can be next to the UPS in a matching design, and just does not have nearly the same requirements as a wet cell. Lately, we have seen some pure lead versions of instead of the lead calcium, of the lead acid, because the battery is essentially just the gap filler. when power fails, the generator starts and it's up and running in less like 20, 30 seconds in most data centers. If it's a hospital, it's less than 10 seconds. But a lead acid, a BLA battery, cannot really be designed for less than 5 minutes because of a coup de fouet. It cannot take a load step just off the cuff. But where pure lead handles that better, pure lead batteries also can be designed to lower run times. They handle temperature better, where standard BLAs are very sensitive to temperature. And then the last one, which is I believe the future, and we've seen over the last couple of years, lithium-ion batteries have gained a lot of popularity. The NFPA threw a little bit of a wrench into this last year when they passed the 855. We've all seen the pictures of burning Teslas and hoverboards and cell phones and stuff like that. The drawback with the lithium-ion battery is when it catches fire, it's hard to put out, and it typically spreads from cell to cell. So NF 855 pretty much required that if you install a lithium-ion battery, that battery cabinet has to be 3 feet away from anything else, including other battery cabinets and the wall and the UPS. So lithium-ion batteries offer a number of benefits, but mainly for a smaller footprint and reduced weight. Pretty good performance also, but with the NFPA 855, the footprint savings was just out the window. There's a way around that, and the entire business is working on getting a UL list, what's called a UL 9540A listing. We have that for the batteries where we are using, but on top of that, and basically the battery manufacturer has to prove that a fault in one battery will not propagate to other batteries. That's the fear, and that was the reason for the 855. But part of this also requires, the UL requires the battery system to be tested with the UPS. That is currently in for ABB, that's in process. We'll be looking at Q3 before we have that work completed. And then the last, which actually is not really that relevant for data center IT application, is flywheels. We see them a lot in like healthcare, hospital applications, but hardly ever in data centers. Mainly because typically the backup time is offered by a flywheel is in the 15 to 20 second range, and you can parallel more to get longer runtime. They start to become expensive, and facility managers, the data center world, have not really. They want shorter run times, like less than 5 minutes, but 15 seconds is that's outside of the comfort level. So that was it. So whatever time is left over, I'm very happy to answer whatever questions you may have. At least try to.
Thank you so much, Jorgen. Let's see what kind of questions we have. Okay, one of the questions is, on the UPS tech side, why is the grounding a drawback on the recent models?
So a transformer-based UPS, and then I'm trying to remember the slides. On a transformer-based UPS, you have what's referred to as galvanic isolation. In a transformer, you cannot. You have a completely separate system on the other side of the transformer. So the one of the benefits with the transformerless system is that the system between, like the UPS, essentially between the input and the output transformer, is galvanically isolated from the upstream and the downstream, which means that the one benefit that you cannot meet with a transformerless is that a transformerless UPS can support a ground fault on the battery, because it's isolated. If you have a ground fault on the battery in a transformerless system, breakers will trip. So that was very important with the wet cell batteries, because people were working around them and were topping up water, and sometimes you had leakage current to ground. with the modern batteries, like with the VRLAs and the lithium ion, that's not really an issue anymore. But that's one benefit with the transformer-based UPS is that you have galvanic isolation between the outside world and the inside of the UPS, including the battery.
Okay, great. Hopefully that answered the question. Here's a question. What is the mean time between failure info for the different types of UPSs that were discussed?
You know what? I'll have to dig that out. I don't. I have some information, but I'll have to dig that up. I can't answer that off the top of my head. It's a so no. Actually, in the interest of time, I'll be happy to dig out find the information, but I don't remember off the top of my head. What, like, the one short note is like same as as kind and can run a lot longer today without needing a major overhaul. Same with UPSs, like with the microprocessor control and the quality control significantly improved overall. MTBF is much better than it used to be. I'll be happy to find the numbers though.
Okay, great. On the modular UPS, are the modules hot swappable?
On the ABB UPSs, I get this. Yes, they are. They're designed to be. They are hot swappable, but doing so, the operator absolutely should wear the appropriate PPE, because you open the door and there's dangerous voltage in there. But you can add a module, you can swap a module on the fly. I've seen it done, and the unit is designed to support that. But I guess I used to say the world was a lot easier before that Irish guy invented arc flash. But of course, it's been around forever, and it's not a bad thing that OSHA is really focusing on that right now. It's not. We've all seen the videos. So does UPS support it? Yes, but it does require the appropriate PPE to do that.
Wonderful. Can you touch on how the UPS is typically maintained? What maintenance is required for the batteries?
Well, with the with the wet cell, I think I probably covered that. That's the topping off the water and just keeping an eye on that everything is torqued and that nothing is changed in color. There's a whole science to that. With a VRLA battery, you really can't see what's going on inside. And so you can clean it. They can be connections can be retorqued. And as the battery changes, or if something starts to go wrong inside, there are a number of different companies making battery monitoring management system that can actually tell if the internal impedance in a battery, if something starts to change, and is going off, and so that the customer or service can respond to that before it creates other problems. But there's not an awful lot, like the usual cleaning, but there's not an awful lot you can do to or see from the outside of the battery.
Okay,
so
great.
That's the battery side. On the flywheel, you change the oil once in a while. Same. It's a magnetic bearing, so that's not really an awful lot to do there.
Sure. Yeah. I have a question. How does the UPS share load in a distributed redundant system?
They don't. Like there's no active load. Like if in the parallel, if you parallel two UPSs, they will actively share the load. If in a distributed redundant configuration, it's up to how you connect the load between all the units in the distributed redundant system. And it'll just be it's a question of load, balancing the load between the UPSs. That is how they don't really know how the load is shared, and that's the actually that's it's a concern. Like I said, we see CATs here, like block redundant and distributed redundant, approximately equally deployed. And from day one is not a problem, but I don't know like that people cannot figure out how to do that. But I've heard several customers raise it as a concern because you never know what those crazy IT guys are going to do. You can add a lot of monitoring, like ABB offers monitoring for our power distribution as well. So you would have all the data, but that's pretty much what it's down to. Is if you know how it has and what the maximum current on each power line is, we can monitor that and then it can raise a flag. But without that, it's a little tricky, and as to maintain the redundancy in a distributed like make sure that you have redundancy in a distributed redundancy system.
Right, because your UPS doesn't tell you that, hey, I'm 80% full of load.
Well, it can. The UPS can tell you that too, actually. But depending on the you have how do I put that? The UPS can tell you how much is loaded. You can get that from with a Modbus or whatever monitoring is used. We can monitor every single power line and the breakers in the distribution as well. So if like the picture I showed with 4 UPSs, if you like shortly just keep an eye on that no UPSs of the 4 UPSs, none of them are loaded more than 75%. You're probably good, except there could be unbalances further down. Even if number one, you don't know how the 4 UPSs are sharing between each other, or how the load is connected. It could be so that if UPS number 3 fails, even if it was balanced when all 4 ran, when one of them failed, suddenly it's not balanced between the remaining 3. So it's a little bit of a science. I talked to a data center manager, said, well, basically he used a spreadsheet from day one and then tried to maintain that. Would think maybe there was an idea in developing a monitoring system that could actually keep an eye on that. I'm not aware that one is available.
Very interesting.
So, but to your point, the UPSs themselves, there's no active load sharing. What we see in a lot of configuration, as I mentioned, like I showed one UPS on the drawing, but in a lot of cases today, that one UPS is actually two 1 megs or 2 1100s in parallel to create a 2 megawatt UPS system. And those 2 UPSs will be connected in parallel. They will share load on a percentage basis between them, and that's active control. In between the different separate UPSs in a distributed system, it's all up to how you balance a load.
Right.
Yes, we'll say before we run out of time, unless maybe we are my contact. I'm very happy to answer questions. If any, please feel free to reach out if you have a question or comment about anything.
Wonderful. Well, I think everybody enjoyed this. It's very informative, and as always, Jorgen, your technical expertise is impressive. So, thank you so much for spending time with us.
Thank you very much, Michael. Anytime, as I said, I'm happy to.
Okay, everybody stay safe and have a great day.
Thank you.